compound, and some of the examples are fatty acids, triacylglycerols, glycolipids, sphingolipids. Okay, and then we have the fused ring compounds. Okay, the fused ring compounds have a very typical fused ring structure. So there are this is a steroid ring structure. Okay, and this is the steroids form the fused ring compound. The most popular example being cholesterol. Okay, so again, keep in mind that lipids are organic compounds that are amphipathic, usually amphipathic in nature, with very low solubility in water, very high solubility in organic solvents, and are mainly of two types: the open chain and the fused ring type. Now, coming on to the main biologically important lipids, these are fatty acids. So what are fatty acids? Again, amphipathic molecules with a carboxylic acid group at one end, which is the polar end, charged, negatively charged, and they have a long hydrocarbon tail. Okay. These are what fatty acids are, basically speaking. Okay, and fatty acids from the living systems. Okay, whether from bacteria, viruses, plants, animals, whatever. Okay, this is important. The way fatty acid metabolism or biosynthesis takes place, it's an addition of 2 carbons to the carboxylic acid group in each term. And that is why the long chain of fatty acids from the living systems are always even numbered. Okay? There are some fungal species that can have odd numbered hydrocarbon chains, but that's an extreme rarity. Okay? So from the living systems, fatty acid hydrocarbon chains, or the non-polar tails, are always even numbered with respect to the carbons. Okay? And most of the time, these chains are linear in nature. They are very rare that the chains will be branched. Okay? Now, we always keep hearing about polyunsaturated fatty acids and the importance of unsaturated fatty acids in the diet. Okay? So if there is a carbon-carbon double bond in the fatty acid side chain or the hydrocarbon chain, it's called an unsaturated fatty acid. Okay, the bond is unsaturated. The carbon-carbon double bond. Okay, if a double bond is present, it's an unsaturated fatty acid, and if there are only carbons and hydrogens, no double bonds, it's a saturated fatty acid. Again, fatty acids, very simply, carboxylic acid containing compounds. The carboxylic acid end is the polar end with a long hydrocarbon tail, which is non-polar in nature. And if there is a double bond present within the tail, it's an unsaturated fatty acid. If there is no double bond, then it's a saturated fatty acid. Now, the stereochemistry, because of the presence of the double bond, changes within the hydrocarbon tail. Okay? And it can be either cis or trans. So your unsaturated fatty acid can be a cis fatty acid or a trans fatty acid. Okay? And that also has a very important structural implication. If there is a double bond present, that usually introduces a kink within the structure. So your fatty acid chain, if it is fully extended, okay, it's a linear, simply linear structure. But if there is a double bond, then there is a small kink within the structure, and the structure twists a little. And that has important implications with respect to the structure of the cell membrane. Okay, we are not discussing cell membranes today. We're just looking at the different fatty acids or the different lipids and their structures only. Okay. Now, how does this name appear? The cis fatty acid or a trans fatty acid. It is with respect to the orientation of the hydrogen bonds around the double bond. Okay. So this is oleic acid. There is 18 carbon, and within the cis form, both the hydrogens around the double bond are towards the same side. Okay. And in the trans form, they are on the opposite What that does, again, if it is a cis form, again, cis form is the major form that is represented within the nation. If it's a cis form, there is a kink in the structure, and that produces a gap within the membrane. If it is a trans unsaturated fatty acid, then if you extend that chain, it pretty much behaves like a saturated fatty acid, okay? Because the chain can be extended into a saturated fatty acid type of structure, okay? Any confusions thus far? Okay? So just remember, if it's an unsaturated fatty acid, it can be both cis and trans depending on the orientation of the hydrogen bonds. That's where the names come from. Cis together, trans different or apart from each other. Now, these are some of the examples of the regularly occurring fatty acids in the nature. The first one is palmitic acid, which is 16 carbon. Now, there is myristic acid, lauric acid, 14 carbon and 12 carbon fatty acids. But the 16 carbon palmitic acid is the most basic example because 16 carbons is usually the smallest number that we see in the chain. Okay? The 16 carbon is the smallest number that is usually encountered. And that is why palmitic acid is the most basic hydrocarbon chain that we see. If there is a single double bond, it is called palmitoleic acid or palmitoleic acid. It's 16:1. And this is the basic nomenclature. Okay? Anytime that you see 16:1 is if there is a ratio sign and the number behind it means the number of double bonds. So if it's 16:1, that means that the chain is 16 carbon long and there is a single double bond. The delta sign and the 9, the superscript 9 means that the double bond is on the 9th carbon. And the counting of the carbon takes place in this kind of a nomenclature. Okay? This is called the delta nomenclature. In this nomenclature, the carbons are being counted from the carboxylic group. Okay? So the 9th carbon has the double bond. There is another classification, it's called the omega nomenclature. In the omega nomenclature, you count the carbons from the chain, not the carboxylic acid group N. Okay? We're not concerned with that at the moment. Again, so keep in mind, anytime you see a ratio sign with any number behind it, that means the number of double bonds, and any number which is superscripted to the delta sign, that means the number of carbon, the number carbon where the double bond is present. Okay, and then more biologically relevant fatty acids are the 18 carbon chain fatty acids, and the most basic of them is stearic acid. And if stearic acid has a single double bond, it's called oleic acid. Okay, oleic acid is 18:1, is a single double bond, and again delta 9. Now, the way the enzymes are set up, again, like I said, the lipid or the fatty acid chains are being synthesized by 2 carbons being added each time. Okay, that's how you have an even number. So, if you add 2 carbons to palmitic acid, you end up with stearic acid. If there is a double bond, it's called oleic acid. And the most abundant enzyme that actually induces a double bond within this chain is has an activity for the 9th carbon. That is why you find that it's delta 9. Most of the time, when you encounter fatty acid structures, there is an exception. It's called arachidonic acid. We're not looking into that. But delta 9 or the 9th carbon is the first carbon where the double bond is introduced. Okay. Looking at a few essential fatty acids, okay. Linoleic acid and linolenic acid. What makes them essential?
That means you can't make them yourself, you gotta eat them.
Because the animal bodies cannot produce them. And these 2 fatty acids alone are the reason why you should have a vegetarian diet, or semi-vegetarian. Okay. don't skip the lettuce in your burgers. Okay? The idea is, in linoleic acid, it's 18:2. There are two double bonds, delta 9 and 12. Okay? So, the 9th carbon and the 12th carbon have the double bonds. And linolenic acid is 18:2. Oh, I'm sorry. I wrote 18:2. I'm sorry. It's 18:3. Please make that change. Okay? 18:3, delta 9, 12, and 15. Okay? So please make sure that you change this. It's 18:3, not 18:2. Yes.
What you're saying is too, that 18 is the number of overall carbons in the chain. So it's not like there's 18 single bonds and 2 double bonds. There's 18 carbons.
18 is the number of carbons.
Okay.
Okay? And the ratio sign, and then 2 means how many, or the number behind that sign means how many carbons have the double bond. Okay? Again, so this is important. Keep at least, if nothing else, keep these two names in your mind. Linoleic acid and linolenic acid. 18:2 and 18:3. Delta 9, 12, delta 9, 12, and 15. Okay? Now, another important point, what is the importance of having an unsaturated bond? The unsaturated fatty acids, as compared to their saturated counterparts, they have a very low melting point. And that is the reason why you have your plant-based oils. Okay? If you do some kind of cooking, any kind of cooking, you will know that your canola oil is always liquid, no matter what. And if you have a box of lard, which you should not, you do, it's always solid. Okay? That is the idea. The plant-based fatty acids or plant-derived fatty acids are extremely high in unsaturated fatty acids. Okay? And is there an exception to that? Good. Coconut oil. Okay? Coconut oil is like crazy oil and extremely rich in saturated fatty acids. Okay? It has a very low proportion of unsaturated fatty acids, and that is why if it gets just a little bit cold, turns into a solid very fast. Okay? So the idea why plant oils are always liquid at room temperature is because they have a very high proportion of polyunsaturated fatty acids. Okay? And the unsaturated fatty acids, okay, the plant oils can very easily be converted into saturated fatty acids by a process called hydrogenation. That is, you just give them high pressure and add a bunch of hydrogen to it, and it turns into, all the double bonds are saturated, and it turns into a mixture of saturated fatty acids. The popular example being? Crisco. Know the word for Crisco? Yes. Yes.
Oleo.
Yeah, oleo margarine. Okay. So again, margarine is, and that was the idea behind margarine, was that they processed it by hydrogenation, and because it was being derived from plant oils, it turned out to be extremely cheap as compared to butter. But then it turned out that you were giving a whole generation atherosclerosis, and it's killing them. All right, now coming on to triacyl glycerol, or what are triacyl glycerol. Okay. The important point to remember is that we were talking about fatty acids up to this point. Okay, there are free fatty acids within the nature, but extremely rare. Okay? It is usually some kind of a stress condition when the cellular system would start releasing free fatty acids. Okay? Most of the time, fatty acids are conjugated to glycerol. Okay? Now, glycerol is the simplest structure that can carry 3 alcoholic groups. Okay? 3 OH groups. So basically it's a tricarbon structure: CH2OH, CHOH, and CH2OH. Okay? So when you have fatty acids forming ester bonds with glycerol, that is, they are removing the H from the OH groups and forming an ester linkage with the glycerol, you end up with triacyl glycerols. Okay? If all the 3 OH groups are replaced by fatty acids, or are esterified to fatty acids, you end up with triacyl glycerols. Okay? And triacyl glycerols are, at least in the animal systems, okay, they are mostly used for storage of fats. Fats are stored within the adipose tissue or the adipocytes in the form of triacyl glycerols. And in plants, they are an important part of the cell membrane also. Okay? Now we're going to just look into some derivatives of the glycerol structure. Now, the triacyl glycerols, because they are the biological form of lipids, all the other fatty acids are also biological forms, but biologically relevant or biologically functional forms of lipids. You can, get both glycerol and fatty acids. You can cleave the ester linkage, and that can be done by two processes. Either it can be done chemically or in a physical manner. The process is called saponification, or you can have specialized enzymes called lipases, or in this case phospholipases. We'll come to that. Okay. Lipases, again, are particular. There are particular lipases for each of the ester linkage. Okay, PLA, PLA2, PLC, PLD. Okay, just means lipase. Okay, and saponification is the process wherein if you have a triacyl glycerol and you provide the system with very high amount of salts, the salts can hydrolyze the ester linkage between the fatty acid and the glycerol, and you end up with glycerol and a crude mixture of what? Soap. Okay, this is how you make soaps. Okay, you take a bunch of lard and you just add salt to it. That's how you get soaps. Okay, and this thing that you see, if you have very hard water in your water supply, you add soap to it. So all the soap scum that you see is nothing but a mixture of fatty acids from that soap. Okay, conjugating with the calcium in the hard water supply and the magnesium also. All right, so coming on to phosphoacyl glycerols. Okay, phosphoacyl glycerols, again, now we are just looking at derivatives of triacyl glycerols or glycerol structures. Okay, so if you have phosphoric acid forming an ester linkage with one of the carbons in the triacyl glycerol, instead of 3 fatty acids, you have only 2 fatty acids, and one of the carbons or one of the methyl groups is forming an ester linkage with phosphoric acid, you end up with phosphatidic acid or PA. Okay? Again, phosphatidic acid is very important, at least in plants, okay? Because it acts as a signaling molecule during stress. Right? Remember this, one of the carbon or the methyl groups is esterified to a molecule of phosphoric acid instead of fatty acid. You end up with phosphatidic acid or basic phosphoacyl glycerol. Okay? Now, this fatty acid also has an alcohol group here. Okay? If this alcohol group or this hydroxyl group forms another ester linkage with whatever, okay, it can form an ester linkage with glycerol itself, it can form an ester linkage with another phosphoric acid, or it can form an ester linkage with a fatty acid, okay, a carbohydrate group, amino acid. Okay. Those derivatives are called phosphatidyl esters, okay, and they are very important biologically. We'll be looking at some of them. Again, keep in mind, phosphatidic acid is the basic structure of phosphoacyl glycerol, wherein one of the carbons is esterified to phosphoric acid, and the rest two have fatty acids attached to them. Okay? And this phosphoric acid group also can form an ester with this alcohol, with anything else, and that is called a phosphatidyl ester. Okay? Now, some of the popular or biologically relevant, biologically functional, very important signaling molecules, structural components of the cell membrane are all phosphatidyl esters. Okay? The first example is phosphatidylcholine. You have a choline group making an ester linkage with the phosphate. Again, in all of these structures, you will find the common thing is phosphatidic acid. Okay? So if you encounter this, or if I ask you a question as to what this is, the only thing that you need to keep in mind, okay, are these groups that are forming an ester linkage with the phosphoric acid. Okay? If you look at it here, this whole thing is phosphatidic acid. Here, whole thing is phosphatidic acid. Up there, phosphatidic acid. Again, phosphatidic acid. So, if you have a choline group, it becomes phosphatidylcholine, EP. If you have a serine, it becomes phosphatidylserine. If you have ethanolamine, it becomes phosphatidylethanolamine. If you have inositol, which is a 6-carbon ring structure, it is phosphatidylinositol. And if you have, like I said, it can be glycerol also. If the phosphate group esterifies with another glycerol, it becomes phosphatidylglycerol. Now again, PC, PS, PI, PE, PG, they are all extremely important components of the cell membrane in both plants and animals. Okay? The idea is there are particular enzymes which can cleave these groups that are esterifying with the phosphoric acid, and then these groups on their own within the cell can act as important signaling molecules during stress or various different physiological conditions, metabolic conditions, especially phosphatidylinositol. Phosphatidylinositol, once it has cleaved the inositol molecule by itself, and then the PA or the phosphatidic acid, both of them act as second messengers for calcium signaling. Calcium signaling is extremely important for muscle movement and brain functions. Okay? So that's the idea behind having a common structure. And again, this gives you an idea as to how the cellular machinery works, or how the work is being cut down for the cell. Okay? To generate phosphatidic acid is very simple for the cell, just 2 reactions. Okay? And then you have this one basic skeletal structure that can keep reacting with different R groups, okay, choline, serine, inositol, okay, and generate. So you basically have an assembly line where you have phosphatidic acid being generated continuously, and then depending on the function of the cell or the function for the cell, you can attach different R groups to the phosphatidic acid. Okay? This is how division of labor works in the cell. You usually have skeletal structures floating around that are used by various different processes. Okay? Make sense? Phosphatidyl esters, this part. Again, the only thing that you should really worry about from this thing is at least acquainting yourself with the structures at this end. Okay? What is inositol? What is serine? I mean, you should know what serine is. Okay? Ethanolamine, choline. Okay, coming on to some specialized lipids. Okay. First example are waxes. Now, waxes are not, an example of triacylglycerols. Waxes are usually just a very complex mixture of long-chain carboxylic acids or fatty acids and long-chain alcohols. Okay, so the end group or the polar head group, okay, is usually either the carboxylic acid group or the hydroxyl group. Okay? And the only defining feature of waxes is that they are a heterogeneous mixture wherein you have very long chains. Okay? And these long chains are usually over 22 carbons. Okay? And again, we all know, both in plants and animals, waxes are secreted towards the outside of the cell and mainly towards the end, which is exposed to the elements, and waxes form a protective layer, protective hydrophobic layer, which protects the cell from any kind of desiccation. Okay? On the leaves of nearly all the plants, okay, you have a very thick waxy layer. The other example is of a different lipid, are the sphingolipids. Okay? Now, sphingolipids, if you just look at the structure, it can be a bit confusing at times because the way it is written is that they show these 3 carbons at the end. And so it might look that the sphingolipids are derived from glycerol, okay? But this whole thing is just one huge linear structure, okay? So you have 12, 13, 14, 15, 16, 17, and 18. It's an 18 carbon linear structure, okay, which is called sphingosine, okay? And you just show these 3 carbons here at the other end because this 3 carbon end behaves like glycerol, okay? So you can have ester formation here with any kind of a carbohydrate molecule or an amino acid, okay? Or you can have amino acids attaching themselves to this NH2 group, okay? That's why this 3 carbon structure is shown separately or bent from the linear structure. And the derivatives of sphingosine are called sphingolipids, and they're found very commonly both in plants and animals, okay? And the sphingolipids that are most commonly found in the animal systems are very abundant in the nervous system, within the nerve cells, okay? And if they are present in the nerve cells, they are called ceramides, okay? Ceramides, okay? Ceramides, again, keep in mind, are sphingolipids. So now coming on to what are glycolipids. The name suggests if you have a carbohydrate molecule attaching itself to a lipid molecule, a fatty acid molecule, you end up with a glycolipid. Okay? The alcohol group is replaced by a carbohydrate molecule. And the most naturally occurring glycolipids are all derivatives of ceramides, okay? And as I said, ceramides are derivatives of sphingosine, okay? Again, glycolipids are very abundant in the animal system. There are examples of glycolipids within the plant systems also, but most of the studies have been done in animal systems. And the most popular one are glucose derivatives, which are called glucose cerebrosides. Like the name suggests, cerebroside, they are very abundant in the cell membranes of brain cells. Okay, that's the main function. They are a structural component of the cell membranes of the nervous cells, mainly the brains. Okay, less so in the nerve cells. Again, it's just a glucose molecule. The simplest of them, which is called glucose cerebroside, is just the ceramide. Okay, so you can see that the ceramide has towards the last carbon of the sphingosine, there is a huge carbon chain attached to it. And then if the other end, the third carbon, has the alcohol being replaced by a glucose, you end up with glucose cerebroside. Again, this is something that I will emphasize again and again. If you are when you look at lipids or any chapters related to lipids, it can be a bit daunting if you look at their structures. Okay? They can be very easily confuse you. So the simplest point is that just remember palmitic acid, 16 carbon, oleic acid, or stearic acid, 18 carbon, oleic acid is 18:1, okay? Linoleic acid is 18:2, linoleic acid is 18:1, linolenic acid is linoleic acid is 18:2, linolenic acid is 18:3. Okay. Keep in mind the biologically relevant lipids, 16 carbon, 18 carbon. And then the unsaturated forms of the 18 carbons, 18:2, 18:3. There is 18:4 also, arachidonic acid, don't bother with that. Okay? And then, when you have that in mind, the other structure that you should keep in mind is the structure of glycerol. Okay? And the most important linkage that you should keep in mind is the ester linkage. Okay? So you have fatty acids, which have carboxylic acid in one end, and long carbon chain, 16, 18, doesn't really matter. And if that carboxylic acid group from the fatty acid is forming an ester linkage with the glycerol, you end up with triacyl glycerols. Okay? Then in triacylglycerols, if one of the carbon is not attached to a fatty acid but to a phosphate or a phosphoric acid group, you end up with phosphatidic acid. Okay? So you have some very basic skeletal structures to keep in mind. Just remember glycerol, or how many carbons are present in the long chain of the fatty acid. If you keep that in mind and look for those motifs being repeated in the various lipid structures that you look around. Okay? And when you see those common structures being repeated, it will be very easy for you to remember any kind of structure. Okay? Like in this case, if you remember